students, welcome back to our course Environmental Modeling and Simulation, and today we will continue our discussion on bifurcations in 2D systems. In the previous lecture, I introduced you to a model which resembles 1D saddle node bifurcation with the difference that it actually has a second dimension, a second variable y, which undergoes very simple dynamics. And then we looked at what happens when the parameter a is bigger than 0. We found out that it will have two fixed points. The smaller fixed point minus a root 0 is a saddle, and the bigger fixed point root a0 was a stable fixed point. Now we look at what happens as we change the value of a. So as a recap, our model was dx by dt is equal to a minus x square and dy by dt is equal to minus y. And when a is greater than 0, the phase portrait is something like this: stable fixed point, saddle. So here we have a saddle and here we have a stable fixed point. The stable manifold is here, the unstable manifold is here. So the trajectories look something like this. Now clearly this is a stable fixed point, so it is an attractor, it is attracting flow lines. So this flow line will eventually join in here, and its eigenvector were also parallel and coincident with the coordinate axes, coincident with the x axis and parallel to y axis. Now depending upon the value of a, we notice that the trajectories would either be tangential to the x axis or tangential to the eigenvector that is parallel to y axis. As we reduce the value of a, what we notice is that they will switch the eigenvector to which they are going to be tangential. This is what we saw in the last class. So now what we are going to do is we are going to start reducing the value of a, and so that a becomes equal to 0 and then less than 0. So we are varying one parameter in this 2D system to see how that variation in this one single parameter is going to affect, if at all, the behavior and the properties of the fixed point. So as we reduce the value of a, we notice that the trajectories become tangential more and more to the x-axis, which is a slower eigenvector. So this is how our phase portrait will look like as we take the value of a and reduce it. Now what happens is that when we reduce the value of a, we will notice that minus root a and root a will become closer to each other. So what we see is that these two fixed points will approach each other, and then like so, and then eventually when a is equal to 0, these two fixed points will coincide with each other because a will be equal to 0 and they will meet at the intersection of the two coordinate axes. In that case, we will have only one fixed point here. And now we want to ascertain whether this is a stable fixed point or an unstable fixed point. Now what happens as these two will come together, we will see that on, now notice one thing, this particular fixed point in the direction of x-axis has unstable manifold. This fixed point in direction of x-axis has a stable manifold, and when they do coincide, what we will get is a half stable, half unstable fixed point with a very peculiar behavior around trajectories, around it. So this half of the fixed point would be a stable and this half of the fixed point would be unstable. So what we will see is that trajectories still are tangential as they approach this fixed point to the x-axis. And what we will see in this direction is that here also they are moving towards the fixed point. However, here they are unstable, so they are moving away. So basically what has happened is we have taken this half of the system and then this half of the system, and they have collapsed into each other to give us this when a is equal to 0. Now what happens when a is less than 0? When a is less than 0, we no longer have fixed points. Now what's happening is that these two, the yellow highlighted portions, are further collapsing into each other. And what we get is a very peculiar case. It looks like this. So the flow is again quite similar to what we were seeing earlier. But here we have a very interesting region. This is known as the ghost area. The ghost region. The fixed point has been ghosted, it has disappeared, and the flow lines are still moving, so we are still seeing some kind of flow here. But when the trajectories move through the ghost region, they slow down immensely. So this ghosting area, ghosting region slows down the trajectory. This is the place where the fixed points used to be present, but now they are absent, they are no longer there, they have disappeared. So this is the ghost region. Now as we look into 2D systems, you will notice that this behaves very similarly to 1D systems. First we have fixed points, they collapse into each other and then they disappear. Actually this is the reason why I spent many lectures talking about bifurcation in 1D, because bifurcation in 2D is very similar to bifurcations in 1D, except now we have one additional dimension. Now obviously this was a very easy model. I mean the second equation dy by dt is equal to minus y, which may not always be the case in your environmental models. You might get, or your real life models, you might get more complicated equations for the second variable, but the principles remain the same. If you vary one parameter at one time, the behavior and the number of the fixed points will vary. And yes, we have the same system, the saddle node, the transcritical, the transcritical, subtranscritical, pitchfork. They all will behave similarly as they did in 1D systems. Now let's take another example of a bifurcation in 2D, which is not as simple as this introductory system, but you will notice that it will still behave very much like bifurcations in 1D. So before we move on to the next example of bifurcations in 2D, I want to give you a heads up on nullclines. Now nullclines make our bifurcation analyses extremely easy. If you remember in 1D bifurcations, what we would do is we would draw the curves, find out the fixed points, and then see how fixed points vary, how their behavior varies as we move, as we change the variable. Here, it's because we have two systems. We are talking about 2D models. So let's say the one variable is x, the other variable is y. X and y are changing with time. So if we try to draw a phase portrait using nullclines, we have two graphs of nullclines, and we know that the fixed point is at their intersection. So in case of 2D bifurcations, it's extremely valuable to use nullclines before we jump into using Jacobian and trying to find out the eigenvalues and eigenvector and the behavior of trajectories around the fixed point. So in the upcoming examples, I'm going to use a nullcline method first before we move on to our Jacobian method to understand the phase portrait, to understand how the model is behaving, whether the model gives us reasonable predictions or not. Now, in the example that we just finished, the saddle node model has a very typical behavior around nullclines. So let's say this is your X nullcline and this is your Y nullcline. Right, on some axes, the position of the coordinate axis is not very relevant here. Clearly these two are your fixed points. Now depending upon the flow around these intersection points, now this could be an orbit or a stable unstable node or spiral or limit cycle or a saddle point, could be anything. All the examples that we have studied so far, it could be any of those. However, if this is a saddle node bifurcation in 2D, as you vary your parameter that's causing saddle node bifurcation, you will notice that these two fixed points will start moving towards each other. Right, so basically what's happening is that this curve is moving away from the X nullcline. So eventually there will come a time when this curve Y nullcline will be tangential to X nullcline and you will have just one fixed point. And then if this Y nullcline keeps moving away as the parameter changes, then you may have no fixed point. So this is the typical behavior we will see in saddle node bifurcation. And this is very similar to the approach we are going to use in the upcoming models where we try to understand bifurcations in 2D. We are going to draw the nullclines, we are going to see how nullclines move as the parameter changes, and that will inform us about the behavior of the fixed point. So let's get started with our next example of bifurcation in 2D. This model that we are going to cover now is an example of autocatalytic expression of a certain protein. So this is a very interesting scenario where we are actually modeling a biochemical switch, and I'm going to show you how. What is happening here is that if a protein starts getting expressed, its expression process will auto-catalyze further expression of the protein. Now, and I do not expect you to have a biological background, but very briefly, to make a protein or to express a protein in the cell, we need to have genetic coding. So, we need to have DNA, which is the genetic coding of all life forms that we know of. So, DNA is the genetic coding of most life forms, definitely the higher order of life. And then what happens is that the cell will make an mRNA, messenger RNA, which is a copy of DNA, looks chemically slightly different. mRNA is not designed to last long. DNA is designed to last for the entire longevity, entire lifespan of the cell, of the organism. But mRNA is not designed to last that long. And then once the mRNA is formed, which is a replica of a part of the DNA, then the cell machinery kicks into action, the cell protein making machinery. What they will do is they will read that machinery, that big, and the machinery is also made of proteins, but that machinery starts reading the code in the messenger RNA, in the mRNA, and starts making protein block by chaining each amino acid together. And then that chain of amino acid configures itself spatially and turns into a functioning protein. This process is known as protein expression, this particular process. So, protein expression is referred to cell making protein based upon the availability of messenger RNAs. As I said, mRNAs don't last very long in the cell. They're not designed to last very long. So, we don't have an infinite production of proteins in the cell, which could be very dangerous for the cell. Now, what the model that we are going to look at is talking about is autocatalytic protein expression. So, what is happening is, let me write this down. Now, what is happening here in autocatalytic protein expression is that once the mRNA for this particular protein A starts being made in the cell, we start getting expression of protein A. The more protein A is made, it triggers more production of mRNA. So, basically if we talk about it in terms of autocatalysis that we studied in case of chemical reaction, what is happening is mRNA permits the cell, it's not transforming into protein, it's permitting the cell to make more protein, particular protein, protein A, and the more protein A we have, the more mRNA is produced, which in turn makes more proteins. This is autocatalytic protein expression because protein is catalyzing its own production. Now, the model that we have used for autocatalytic protein expression looks like this. So, let's say protein is represented by variable X and mRNA is represented by variable Y. By the way, students, if you are more curious about understanding DNA, mRNA, protein business, I do have an NPTEL course, Applied Environmental Microbiology, and I encourage you to take a look at it. There are certain lectures which talk about the basic dogma of biology, where we discuss this business. And for most environmental modelers and mathematical modelers, I must say that the lines between different disciplines like computer science, mathematics, environment, and biology are getting blurred very fast and disappearing. So, we need to learn about different domains. Okay, coming back to our model, the model looks like so. So, this is our 2D model for autocatalytic protein expression. The X here represents protein, as I said, and the Y here represents the mRNA. The more X we have, the more protein we are making, what will happen is dy by dt will go up. Now, the more Y we have, the dx by dt will go up. So, they are mutually increasing each other. Interestingly, so remember, first step is always conceptual interpretation of the model. Interestingly, both dx by dt and dy by dt also have a negative term. So, it is not going to be a vicious cycle where mRNA and protein just feed off each other, and now we have an endless, unlimited production of the protein A, which would be a disease, something not viable for life, something that makes cell non-viable. But we also have limiting terms here. Now, if you look at the limiting terms, dx by dt goes up, increases when y increases. So the production of protein increases as the production of mRNA increases, and production of mRNA increases as the production of protein increases. This is the autocatalytic part. The regulatory part, which prevents excessive production of either x and y, are the minus terms. So let's look at the minus terms. Dx by dt is equal to minus ax. This is your minus term. Basically, if we have too much of protein made, then it will self-limit itself. Dy by dt also has a minus term here, minus dy. So the more the mRNA produces, the more it self-limits its own production. So not only do we have autocatalytic protein expression going on, but we are also having self-limiting behavior from both the protein and from the mRNA. Alrighty, we are going to look at this model, we are going to sketch the nullclines, and we are going to see, is there some level of bifurcation happening here. So let's start with sketching the nullclines. Now if you remember, here is x and here is y. So if you remember, let's draw the x nullcline first, and x nullcline is when dx by dt or x dot, however we put it, becomes 0. So it is the curve given by minus ax plus y. So basically ax is equal to y. So it's given by the line y is equal to ax, and the line passes through center. So this is our x nullcline. Now let's make our y nullcline. Y nullcline is when dy by dt is 0. So you see what we are doing, we are simplifying the system. Individually we are finding out how the nullcline looks like, and at the intersection of the nullclines, both variable growth rate, dynamic terms would be 0. That's our fixed point. Now y nullcline will be when dy by dt is equal to 0. That is x squared by 1 plus x squared is equal to by. So y is equal to x squared by b 1 plus x squared. This is a sigmoidal curve and it will look something like this. So this is our y nullcline. Now notice one thing, for given values of, now x nullcline is basically y is equal to ax. So let's vary and, and y nullcline is y is equal to x squared by b 1 plus x squared. Now let's keep b constant for now, but let's vary the value of a because this is an easier curve to vary. And what we will see is that when a is sufficiently small, we have 3 fixed points. First fixed point, second fixed point, third fixed point. Now as we increase the a, the slope of this line will increase, and there will come a time when the line will be tangential to the curve, sigmoidal curve. So we'll have only 2 fixed points, one would be at 0 and one would be here. And then if we keep on increasing the value of a further, we'll end up with, so this is a1x, a2x, a3x. There will come a time when we'll only have 1 fixed point. So what's happening here? We have 3 fixed points to begin with. As we increase the value of a, the 2 fixed points collapse into each other, and then we have these 2 fixed points disappear. The collapsed fixed point disappears. So clearly this is a situation where the fixed points are collapsing into each other and they're disappearing. This is a case of saddle node bifurcation. So even without finding the Jacobian, without finding the characteristic equation, the fixed points even, just by drawing the nullclines, you can already start telling that this autocatalytic protein expression undergoes saddle node bifurcation. Now, of course, to understand the practical implications of this model and to understand, okay, if this autocatalytic protein expression is following this particular model, what is to be expected as we vary A and B? So for that, we'll have to find the stability of the fixed points. So what we are going to do now is first we are going to still stick with the nullcline method and try to see how we can interpret the graph that we already have to understand better the flow of trajectories around the fixed point. So first we need to find out this critical value of A critical, at which the line becomes tangential to the sigmoidal curve here. Okay, so for that we need to find out the intersection between the two nullclines. So we have one nullcline given by y is equal to ax. This is our x nullcline. And then we have this system here, y is equal to 1 by b x square 1 plus x square, which is our y null plane. At the intersection of these two, we have a fixed point. So for intersection, y and x would be equal. So we get ax is equal to 1 by b x square 1 plus x square. So clearly, x is equal to 0 is one of the fixed points, right? It's always going to be a fixed point. Now let's look at the other fixed point. The other fixed point we'll get is a is equal to 1 upon b x square, sorry, by this system, right? We have taken x common and said x is not equal to 0. So this is definitely one of the fixed point. Now we are going to find the other fixed point. So this becomes very simple. AB 1 plus x square is equal to x. Now this I'm calling it second equation because I know I'm going to use it very soon. Of course, when you're solving such questions for the first time, you do not know, but you need to keep your eyes very open so that you are aware of what you have. And if you need to, you can use them later on. Okay, so this is our system that we get. Let's open the brackets. We get abx square minus x plus ab is equal to 0. This is a quadratic equation. X, the other critical fixed points, will be given by 1 plus minus 1 minus 4a square b square by 2ab. Okay, so these are the other two fixed points. If you remember, one fixed point is here, which is 0, 0, which is always going to be the case. X is 0, and remember, nullcline for x-axis, if x is 0, y has got to be 0. So this is always a fixed point. We are talking about these two fixed points. So these two fixed points, the x value is given by this equation, equation that you derived from this quadratic equation by making the intersection point same. This is interesting because now we have a square root. So depending upon the value of AB, we will or will not have we will have real additional two fixed points, or just one fixed point, or imaginary fixed point, which means no real fixed points. So this part of the equation inside the square root is very important. So basically, when 1 minus 4a square b square is greater than 0, which is 1 is greater than 4a square b square, or a square by b square is greater than 1 by 4. So again, we can figure out what it means for AB. So we know that AB are both positive. So basically, when AB is less than 1 by 2, when this is the scenario, then we know that we have two additional fixed points in addition to 0, 0. When AB is equal to 1 by 2, what happens is this will become 0, and we'll have just one additional fixed point given by x is equal to 2ab. This is when you have a critical case. This is when the line will be tangential to the sigmoidal curve here. So we now know the value of x here. X is given by 1 by 2ab. When we have the critical scenario, and we also know that in this scenario AB is equal to 1 by 2. Okay, so AB is equal to 1 by 2. So if you put this value here, you will get your fixed point. This is the tangential place. Now let us look at the nullclines and figure out the flow of the trajectories around the fixed points. So this is our diagram. X, Y. We have one nullcline, the X nullcline, which is y is equal to ax. And then we have another nullcline which looks like this, which is the y nullcline. Alright, we also figured out the value of a when this line would be tangential to the curve. And we also figured out the value of x for this. But let's just look at the behavior of trajectories when we have three fixed points. Okay, so remember how to figure this out. We have to go through each segment and try to see the value of x dx by dt and dy by dt. So what we are going to do now in the next lecture is we are going to look at each of these segments, the segment here and then this segment, all these segments that these two null lines separate in this graph, and we are going to look at how the dx by dt and dy by dt values are changing and what information it gives us about the flow of trajectories and the stability of these two fixed points. And then we are going to interpret what it means for the expression of the protein, the autocatalytic expression of the protein. So this is all for today's lecture. In the next lecture, we will continue this example and we are going to draw our phase portrait with trajectories and all. See you in the next lecture. Thank you.